And the one constraint that the wave function has, and there's different ways what's the word I'm looking for? Different ways to define this constraint, but this is the one that we're going to use. And it said if you take the square of it, the absolute value, the magnitude square of it, and you look at a small area, right, a small distance dx, right? Maybe it's a one-dimensional particle, it's moving on a line. And we look at what's the probability of finding it in that small part dx. We calculate psi squared. All right, so this is the probability of observing this particle at some position dx. And we can use this immediately to calculate the probability of finding the particle or the system at any position. So like, let's say between A and B, right? We have a line and we cut it from A to B. And we ask the question, what's the probability of finding it in that region? All we do is we take psi squared and integrate it from A to B. All right? And that will tell us the probability of finding the system in that space. Okay? And because it turns out because psi is complex sometimes, it can be a complex valued function. It might have some i's in it. The squaring it's a slightly more complicated. Instead of just taking psi squared, I'll often call it psi squared because often we'll just deal with real functions. So it's equivalent to taking the square of it, is that you multiply the wave function by its complex conjugate, right, which I label star, psi star. And a complex conjugate is very easy to understand. Imagine that you have a wave function here, and this is a wave function for a free particle moving around freely, e to the ikx, where k is a number. So you have an I inside of here, and to take the complex conjugate of it, we just take the negative of the I. All right? So if you have an I in your wave function, the complex conjugate is always minus I, or vice versa. Okay, so it's really easy to do that. And so what we're doing is we're taking the magnitude of a complex function or a complex number, which is where you take the absolute value and square it, which is psi star psi. Okay, and so the other constraint that we do is that the probability has to be normalized. Right? We need to ascertain, our wave function needs to be such that when we calculate the probability of it being anywhere, well, the probability has to be 1. Right? It can't be more than 1 because there's only 100% chance of finding it anywhere. So we'll be able to calculate wave functions, and then we might have to do some math in order to make sure that when we integrate overall space, when we do this calculation of seeing whether if it exists anywhere, that it integrates to 1. Okay. So this is literally the object itself. Right? We've literally defined what it means to be a quantum mechanical object. It has a wave function. We measure its probability, which is measured by the square, or the magnitude squared, and then the probability is normalized. All right, so that tells us what the object is, but the problem is that doesn't tell us how we ask any questions of it. Right? Eventually, we have an object and we want to know something about it, so we have to know what we ask and how do we ask it. And that leads us to the second postulate. So now we can come up with a framework for asking questions. And what we use to ask questions in quantum mechanics are something called linear operators. This is a scary term, but I guarantee you it's not a scary concept. So for every observable, right, everything that we can measure about an object, right, its position, its momentum, its angular momentum, its energy, that's going to be the most important one. Its energy, if we want to ask the question how much energy does a particle have, there's going to be what's called a linear operator associated with that variable. So every observable, there corresponds what's called a linear operator in quantum mechanics. And I will briefly explain what an operator is. You can think of it as a function. Right? It'll take a wave function and it's going to spit a number out. So let's just draw it schematically. So here's our object psi. Right? Here's our wave function. It could be a electron or U, for instance. It can be U. You have a wave function. And we want to ask it a question. Right? Let's ask it, where is it? What's its position? All right? So we're going to feed it into a box, our measurement device, that measures position. Right? And what the linear operator is going to give us is the position out. Right? It's going to tell us what position it's at. And it turns out it also spits out the wave function again. All right, so you're doing a measurement on a wave function, right? You're doing a measurement of the position of this object that's represented by a wave function. This box, the operator, and I'll explain what it means by linear operator in just a second, spits out the position of it, and it gives us back the original wave function. You can think of it, a good example of a linear operator, the simplest one, is addition. Addition is a linear operator. All right, what does addition do? Well, addition is a box that takes in two numbers, A and B, and spits out C, which is A plus B. All right, that's a linear operator. And it takes two numbers and gives you the sum. So you can often write this as plus A, B as a function. It's a function plus that gives you C. Okay? So everything that we do in quantum mechanics, every measurement we take, has this operator, this function, that you operate on the wave function, this box, this black box operation, and spits out a number, which is the thing that we're observing, and it gives us back the wave function. Basically, this operation doesn't change our wave function, doesn't change our particle, right? We get it back, if you will. It's non-destructive, and it gives us a number that tells us something about what we want to know, an answer to our question. The most important thing is that all physical observables, anything that we can measure, must have a corresponding linear operator. Right? There's an example. An example is often when people look at, here's a good chemistry example. If you look at something that's hydrogen bonded, for instance, and if you look at back in literature, people talk about, well, how does the energy of a hydrogen bond between two water molecules, how much of it is electrostatic, how much of it is what they like van der Waals or a London dispersion force, and people come up with these really intricate models to break down the energy as a part of the electrostatic part and part that's not electrostatic. But in reality, those parts are not physical observables, right? The electrostatic energy of a hydrogen bond is not a physical observable because it doesn't have a linear operator. It's just a mathematical trick to split the energy up. The only thing that has a physical observable, the only physical observable which has a corresponding operator is energy, right? So when we go ask the question to the hydrogen bonded water dimer, how much energy do you have stored in that hydrogen bond? The only thing it's going to spit out is total energy. It's not going to tell us anything about how much energy is this kind of force, how much is this force, because those subforces don't have operators corresponding to them. So the questions that you can ask of an object is very limited. And you end up having to do a lot of magic tricks, effectively, different ways to partition things in order to get more information from it. Fortunately, nature is rather simple in its answers. Okay, and so that kind of tells you what an operator is, and now I need to define what I mean by a linear operator.
Professor?
Yes?
So
question.
what exactly is a physical observable?
Anything that you can measure in lab.
Oh, okay.
The position, the momentum, the kinetic energy, anything that you can think of.
Okay.
The angular momentum of an object. Right? Something that you measure in physics or in chemistry. A really good example is how much binding energy is there in a complex, right? Or how much energy does it take to break a bond? That's a physical observable, right? The energy. So anything that you measure in lab, anything that you measure classically, right? Any number that you read out on your instrument has to have a linear operator associated. All right, so let me explain what linearity means, because this is an important point. And it's a good point, even though it sounds like it's more complicated, it makes our life much more simpler. So let me explain what linearity is. So let's come up with an operator, all right, just an arbitrary one. And I'm going to call it A. And when I talk about operators, I'm going to put a little hat on top of it like this. All right, so if you ever see something with a hat on top of it like this, a caret on top, that's an operator. So let A be an arbitrary operator. You can think of anything you want. Energy, position, momentum, whatever. And let's say that when you when you apply this operator to a wave function, which we'll call psi1, this is how we typically write it. We write the operator before the thing that we're operating. It spits out a number. Right, so the observable we get, the number we get as is little a, and it returns the function. All right, so you're going to see this equation all the time. You're going to see an operator operating on a wave function, and it's going to be equal to a number times that wave function. Right? The operator just looks at the wave function and gives you an answer and returns the wave function. All right, and let's also say we have a different object with a different wave function. Let's call this A1 instead. Oh, no, let's just call it A, sorry. That also gives you the same answer. All right, so you have two different objects that give you the same answer when you put them through. Right? Maybe you have two electrons that have the same energy. Right? And you're asking how much energy they have, and it gives back the energy. And it's the same for both. Now, the cool thing about quantum mechanics is that you can also have particles that are superpositions of both, right? Remember that's the experiment we talked in the first lecture about the silver atoms, right? We had half the silver atoms were plus magnetization, if you will, and half were minus. And I said that actually what the silver atoms are a combination of both. Right? So imagine that psi1 is the plus state and psi2 is the minus silver atoms. But silver atoms are also simultaneously both at the same time. So imagine that we had a different wave function that is made up of a sum of these two single wave functions. Right? We have a combination, a superposition of both states. Right? And these C numbers are just weights. Right? Maybe we have 10% psi1 and 90% psi2. It doesn't matter. In the silver atoms, they were half and half. Linearity implies this. We can distribute the A, the operator, into our wave function, like so. Right? So these numbers are just numbers, so we can factor them out, if you will. And we've distributed the operator. Okay, and we can use this rule now to apply this, to solve this, right? So C1, and then and psi1, the operating A operating on psi1 gives you A, and the wave function back. And the same for psi2. Okay? Now we can factor out the A. And look what we've got. We have now the value, the observable, and we have the original wave function back. Okay, this is what linearity means. Linearity means is that if you have an operator that gives you a result for two different things, then you get the same result for a sum of those two different things. Right? So that's what I mean by linearity. Does that make sense to everybody? Okay. Everything in quantum mechanics is linear. We're just going to add things together, and doing mathematics or or measuring things on sums of things is the same as doing it on a single thing. All right? So we can use the laws of distribution and commutation and so on, regular algebra, to do our measurements. So now the question is, what are some operators? What are some things we're going to want to measure? And there's lots of things we want to measure. Maybe we care about motion. Maybe we care about energy, which when we do spectroscopy, that's all we care about. Oh, I can't believe they ruined my board. It's awful. Someone needs to get fired for that, I think. I'm just kidding. I'm not serious about that.
Use of that spray.
Yeah, there was a note here that says, please only use water. So someone used something on it and it ruined the board. So I didn't have enough time to clean. All right, so what I'm going to do is I'm going to give you some examples of operators. All right, and we're going to see these time and time again. And we're going to have basically a toolkit of these boxes to apply to any wave function. So I'll make a little table here. First, we're going to have our observable, right? That's the quantity we want to measure. I'm going to give you a symbol for it, right? What we represented on a piece of paper. and then the actual form of the operator, right? The algebraic form, the formula, if you will, for that operator. All right, and the simplest thing we can measure is the position. Right, where the hell is this object? All right, so let's imagine it's a one-dimensional, right? It's on a line, all right? So don't worry. It turns out that if it's in 3 dimensions, that's the same as it being in 1 dimension. The math just changes slightly. We just add things. So let's just assume it's 1 dimension. All right, the symbol that we're going to measure is x hat. Right, that's our operator. Right, for our position x, if you will. And the operator is very simple. You just apply x. So if we want to measure, if we want to ask the question where our object is, right, what position x it's at, then all we do is we apply the x to our wave function, and we get the position back times the wave function. Really simple. Right? And this also applies for x squared. If you want to look at the magnitude of your motion, then the x squared operator is just x times x. Right? It's just linear. Like that. Right? And so on. Really easy.
Are you dividing by x? Like,
What's that?
It's like the first one you're doing x.
Oh
hat.
no, sorry. Let me just write it like this.
Is it like your?
It's like that's what it means. That's what you would write in classical physics and in Newtonian physics, right? You would just write x. I'm sorry. I'll just leave it like x hat instead.
Okay.
Yeah. All right. So position. Really easy. We'll do it all the time. We want to measure the average position of the how far from the electron on average. Oh, sorry. How far from the nucleus on average is the hydrogen, the electron, and the hydrogen's 1s orbital, for instance, right? We're going to want to ask that question about the hydrogen electron, and we do it exactly this way. We take the 1s orbital, the wave function representing the 1s orbital, which we will do later in this class, and we just multiply it by x, and then calculate the result we get out. All right, so super easy. The next one that we might want to ask, and we won't do this too much in this class, but it is an important one to think about, is the momentum of the object. Right? Momentum in classical physics is the mass times the velocity of the particle. Right? It's how much motion, or how much massive motion an object has, if you will. We call this P. Okay, so there's our P hat. And it also has a very simple form. It looks different than m times v, though. And that's just because it's quantum mechanics. And so I'm just going to do it in 1 dimension for now. And this is equal to minus I h bar times the derivative with respect to the position. All right, recall that h bar, is Planck's constant divided by 2 pi. Okay, so when we want to ask a wave function what's its momentum, we multiply it by minus I h bar, and then take the derivative. All right, and that will spit out a number times the wave function, the original wave function as we showed here. And that number will be the momentum of that object. We won't look at momentum too much because we're not physicists, right? We don't really care so much about the momentum of objects, but maybe if you're doing scattering, right, if you're colliding molecules together, momentum will be important.
Professor,
Yes?
are you saying I because it could be complex?
Yes, momentum in fact is inherently complex.
Okay.
And the reasons for why that is very technical. Hopefully we will talk about that at the end of this class or next class.
Okay.
Yeah, so this is the important part about quantum mechanics. Unlike classical physics, there are complex numbers. And that's because everything is a wave, right? We're going to represent molecules and objects, electrons, as waves. And electric waves are often complex value. And so so I's come into play here. Another one that we might be interested in is the kinetic energy. which we call T. I have no idea why it's called T, but it is. And T also has somewhat of a complex result or number or representation.
That was like the tau.
It's h bar minus h bar squared divided by 2 times the mass of the particle times the second derivative with respect to position. So if it were 3D, it would be the sum of the derivatives with respect to the positions. Okay. This is also equal to, it turns out, negative momentum squared divided by 2m. All right, so that's how you derive that. All right, so momentum is a single derivative, and energy is a square of momentum. So you get a second derivative effectively. Okay. And I'll start this on the other side too. We're going to see this kinetic energy a lot because it's about to be, in fact, it's going to be our best friend because we're going to be able to, using this formula for kinetic energy, we're going to be able to calculate the total energy. That's going to be kind of like our magic operator. And it's going to be the thing that we're going to use to calculate wave functions of systems. Because what we measure in lab, really, in the end, is energy. Right? We care about the energy of our objects. Spectroscopy is observing the change in energy in objects. Very often, that's the way it's considered. So we're going to want to ask a lot of questions about energy. Right? And then maybe another type of energy that you care about is potential energy. Potential energy can be anything because it depends on the system that we're in. For instance, if it were a free particle, right, it's just moving around in space by itself, there's no potential energy because there's nothing attracting it. But maybe it's close to another object that attracts it electrostatically, right, because of charges. Or maybe you want to put the particle in a box and lock it in the box so it can't get out. There's going to be potential energy associated with that. And so we call this, by convention V, and V is just whatever the potential energy function is, right? So we just have to define it for our system, right? So it could be a box, it could be a circle, it could be a sphere, right? It could be the attraction of two atoms together, right? The electrostatic attraction of two atoms. Or we could come up with all sorts of potentials, right? This tells us about the environment in which we have our object, right? And it's just some function, right? And then finally, we'll talk about more operators later, but this will be enough for now, is the total energy, which we write as H. And I'll explain why in just a second. And H is just the operator T plus the operator V, right? It's the sum of the kinetic and the potential energy. Right? That's all the energy we have. H is our best friend. H is called H because it's called the Hamiltonian. Now, I'm not sure you guys ever learned this in physics, but there's different ways to come up with the model for classical physics, right? You learned about Newtonian physics, right? You learned about Newton's laws. And a couple hundred years later, in the late 1700s and 1800s, there were two physicists, one who was British named Hamilton, and one that was called Lagrange. He was French. They came up with different formulations of physics. And Hamilton did all of his physics by solving for the equations of motion using this total energy, the Hamiltonian. All right, so we use that in quantum mechanics because it's easy. And it's easy to understand, right? We want to ask the question, how much total kinetic energy and potential energy we have? Let's just add them together as an operator, right? So we call that the Hamiltonian. And the Hamiltonian is our best friend. We're going to do everything with that. Every question we're going to ask about everything. Well, what's the energy structure of the hydrogen atom, right? Or what's the energy structure of a molecule, right? Or how much binding energy there is in a bond. We're going to ask it with the Hamiltonian, right? And the wave function will be whatever system we're looking at. And so the Hamiltonian, just as a reminder, just to add it together, is going to be minus h bar squared over 2m times the second derivatives with respect to space, or the curvature, if you will, plus the potential energy. All right, it's just T plus V. Okay, we're going to see this time and time again.
So are these
Yep.
used like interchangeable functions to like add on to stuff, or
Which ones in particular?
I was sort of getting a blanket statement, but now
Oh.
I'm guessing that's not the case.
So think of it as these are questions that we can ask physical objects, right? And these are the most common things that we're going to ask physical objects. We're going to ask it, where is it? How fast are you moving? How much energy do you have? And these are these boxes, right? They're just mathematical formulas that we apply to a wave function, and we're guaranteed that if the wave function is a solution for this, it's going to spit out a number that gives us whatever the observable is, energy or position or anything like that. Right? So what we're going to do is we're going to come, so for instance, like for hydrogen atom, right? So when we come to the hydrogen atom, we're going to represent the hydrogen atom as a ball with positive charge, right? The nucleus, a proton, and right? There's a proton in the middle, and there's an electron orbiting around it. Right? So there's going to be we're going to want to know what are the energy levels that the electron can be in, right? Which we know is the 1s orbital, the 2s orbital, the 2p's, right? Those are all the different different states the electron can be in. And in order to define those states, to even know what a 1s or a 2s orbital is, we're going to first come up with a potential energy function that describes the attraction of the nucleus to the electron. And we're gonna solve it. So let me actually write this down real quick. So what we're gonna do is we're gonna come up with a potential. Right, so there's our energy, right? We've come up with some potential that describes the attraction of the electron to a proton, plus the kinetic energy of the electron orbiting or moving around the proton. This is just the kinetic energy of it. And the equation we're going to want to solve is this. We're going to want to come up with a set of wave functions. Right? These are the things we're going to solve for, such that when we apply the Hamiltonian to that wave function, we operate on it, we get a number back. Right? So this is an equation. This equation we're going to solve, this is the unknown. And the constraint is that when we apply this operator to our unknown wave function, we get a number back. Right? And we're going to come up with different ways to solve this in order to come up with wave functions that satisfy this equation. Does that make sense to everybody? We're going to see it in examples, so just hold on. When we start doing problems, it'll become much clearer. So you have this algebraic equation that we say, okay, this operator applied to some unknown wave function gives us a number back times that wave function. Knowing this, we're going to solve this equation so that we find the wave functions that satisfy this. And this equation is extremely important. This is called the Schrödinger equation. Named after Erwin Schrödinger. And this is our key tool for determining what a function is, or what our system's wave function is, or what are the wave functions of our system. We know what the box looks like. We've developed the box to ask the right question, this operator. We know that it should give us back a number. And knowing that constraint, we can solve for the wave function. And that's exactly what we're going to do. All right, so this seems kind of abstract, but we'll come to real problems very soon. And you'll see how this works in practice. Questions? Yes, ma'am.
What was
The mass of the particle. Yeah, mass of the particle. Yeah, so when we do the hydrogen atom, we're going to be looking at the motion of an electron, the energy of an electron, so m will be the mass of the electron, if you will. Okay. All right, so that's an operator. All right, that's the magic. This is our measurement tool, if you will. So it's a little different than regular physics, because the motion of a particle in classical physics always has its position and time encoded into it, right? When you calculate the trajectory of a particle moving from out of a cannon, right, with gravity, you always know the position at all times. That's a whole part of the solution. But we don't always know that with a wave function. In fact, what we're going to find is that there are times when the position of something is completely undefined. All right, and we'll see that very soon. Okay, so let me follow up with the next one. Postulate 3. And I'm going to introduce a term of postulate 3 that seems strange. And it's not really an appropriate way to use it, but it's just by convention. And it's the idea of eigenvalues. It's kind of a strange term. So if in any measurement of an observable corresponding to some operator, let's just call it A. The only values that you will ever see in your instrument are called the eigenvalues of A. Okay, so let me show you what that means. So again, let's go up with our equation that we've seen already. We have an operator operating on a wave function, and it gives us a number back times that wave function. This value A is called an eigenvalue. And it's the only thing you're ever going to observe. Right? You're never going to see a number that's different. Right? If you see a number that's different, then that means the wave function of your system must not be what you think it is. All right, so this equation, where you take an operator, apply it to your function, and you get a number out times a wave function, that's the number. That's the only number you'll ever observe. So for instance, the hydrogen 1s orbital. Right? Hydrogen 1s orbital, or let's say the 2s orbital, rather. Think about the hydrogen 1s orbital being at zero energy, right? It's the ground state. Then there's the 2s orbital. Right? And you're going to ask the question, what's the energy of the 2s orbital? Right? You're going to apply the Hamiltonian to it and get a number out, your energy. That energy that you get from that Hamiltonian is the only number you're ever going to measure. Right? The energy of a system is unchanging in time, effectively. Right? And that number, that energy is completely specified by the wave function of that 2s orbital, that state. Right? So that guarantees that no matter what we do, if we have a well-defined wave function for our system, we're guaranteed to always see the right result. However, there might be a possibility that an operator has many wave functions that satisfy this. So for instance, the Hamiltonian for the hydrogen atom has tons of wave functions that satisfy the Hamiltonian equation, the Schrodinger equation. There's the 1s orbital, there's the 2s orbital, there's the 2p orbital, there's the 3s orbital, the 3p, the 3d, the 4s. Right? There's an infinite number of hydrogen states, and they each have their own energy. Right? And what this tells us is that whatever state we want to look at and ask how much energy it has, it's always going to give us the same answer back. So in general, an operator will have potentially an infinite set of eigenvalues corresponding to an infinite set of what we call eigenfunctions, which are the wave functions. So apply our operator A, we might have a bunch of wave functions that we can label with an integer n. And it's going to give us the eigenvalue associated with that function. Okay? So think about again like the hydrogen, right? The hydrogen atom. You have a 1s, a wave function representing 1s orbital, one for the 2s, one for, and so on. Right? And depending on which wave function we ask, which state we ask its energy, we're going to get the energy back for that one. Right? So there might be an infinite set of solutions for this equation, if you will. We often call the set of eigenvalues that satisfy this equation. Right? I'm going to call it the set of A sub n, right? The observables, the eigenvalues. It's called the spectrum of A, of the operator A. Right? You can already start thinking about spectroscopy, right? Spectroscopy gives you the energies of all the levels of your atom or your molecule, the energy levels of your molecule or your atom, right? And when we observe that, that's our spectrum, right? That's the spectrum of the Hamiltonian. We're literally using spectroscopy to measure the spectrum of the Hamiltonian applied to our quantum system. So we're going to get some, we could have, and again, the hydrogen atom has infinite number of states. Eventually the states get so energetic that the electron effectively leaves the atom. But in reality, there are an infinite number of orbitals in the hydrogen atom, or any atom. And if we let A be H, the Hamiltonian, then that set of eigenvalues, the spectrum of the Hamiltonian, is the whole set of energy states that our atom or a molecule can be in. Right, which is why we often call spectroscopy why we call it spectroscopy, because we're measuring the spectrum of the Hamiltonian. Questions? Okay. All right, so when you apply, just as a reminder, the most important eigenvalue equation in this entire class is applying the Hamiltonian to some wave function and getting the energies back. So this could be, again, our 1s orbital, 2s, etc. And these are the energies of the orbitals. All right, we're going to see that when we get to the hydrogen atom. Okay. All right, grinding through. We're about halfway through them. Hopefully we'll get through all. They get simple. Another one is calculating averages. Average observables. Maybe we want to calculate the average value of the position of the electron in the hydrogen 1s orbital. Right? What position is it on average? Right? And so we need a formula to calculate an average. All right. Because the electron can be anywhere. It can be it could be, again, as I said, 10 light years away, or it could be, an angstrom, a tiny amount of place away from the electron, or so from the nucleus. And maybe you want to ask the question, where is it on average? So if a system is in a state described by the wave function psi, then the average value of an observable, like its position, has a very simple formula. So an observable corresponding to operator A is this. We write the average value in brackets. So here's our average value of A. Let's just say it's x for now, for example. All right, we want to calculate the average position of something. And the way you do that is you take the integral over all space. So we'll do from minus infinity to infinity of psi star. Right, that's our wave function, times the operator associated with your observable, so in this case x, applied to psi dx. Okay, so we just take that probability integral that we showed in the first postulate, and we sandwich an operator in the middle of it. Okay, and I think on the problem set, and certainly if not on this one, it'll be on the next one, we're going to want to calculate average quantities all the time. And a great example is well, what's the average distance between the nucleus and the electron? Right, that's going to tell us a lot about the structure of something. And so anything that you have, any operator that you have, and you want to calculate its average observable, you just stick it in the middle and integrate. All right, we'll see some cool examples of this soon. All right, that's postulate 4, super easy. Hopefully, on Monday, we'll look at our first example of a quantum system, and we'll be able to calculate this with relative ease. All right, here's another interesting one that's totally quantum mechanical and it has no corresponding reality in the world that you understand classically. And it's called orthogonality. Okay, assume you have two wave functions, psi m and psi sub n, right? Two different states. I think the 1s and the 2s orbital, for instance, the hydrogen atom. Are wave functions, or eigenvector, or eigenfunctions as we often call them, that satisfy the following properties. Apply an operator A to psi n, and you get some eigenvalue a n for that. And you apply it to the other one, psi m, and you get an eigenvalue a sub m for psi m. Okay? And let's assume that n is not equal to m. Okay? All right, so you have two different wave functions that give you two different values, right? Two different observables. Right? Or like, 1s and 2s give you two different energies. Then the integral, right, we calculate basically the probability integral, but we take psi star of m and multiply it by psi n dx over all space. This is necessarily 0. What this means is that if you have an operator that has two wave functions that satisfy the eigenvalue equation here, there is no probability or spatial overlap between the two. They don't interact at all, right? What this means is that when you have, for instance, in the hydrogen atom, and this is an example I'm going to come back to time and time again, you have a 1s orbital and you have a 2s orbital. They don't interact at all. In fact, they don't see each other as if they don't exist. Right? There's no, if an electron's in 1s orbital, there's no probability it's going to be in the 2s orbital unless you do something to that atom. Right? States are orthogonal, which means they don't interact. Right? So they have no overlap with each other. They cancel out. Right? This makes our math really, really easy. Right? Because we know if we're curious about an electron in a 1s orbital, we want to make sure that that electron is in a pure state, right? That it's not interacting and talking to the other states in the atom. It's just there by itself isolated. And that's exactly what this guarantees. There are going to be two different states that satisfy this equation, and they're not equivalent. I'm going to write a n is not equal to am, right? They give you two different energies, for instance. And you're guaranteed that these states are orthogonal, which means they don't overlap each other at all. They don't talk. They don't even know they exist, each other. It's not until the only way you can get an electron from the 1s orbital to the 2s orbital is that if you excite it, right? If you put some energy into it, right? You have to modify, you have to perturb the atom in order for that electron to move from one orbital to another. But in the absence of that, right? Like the hydrogen atom floating in the void by itself, and it's in a ground state, right? It's on average sitting in the 1s orbital. It has no concept of the other orbitals around it. In general, this is just a notation, because you'll see it a lot in the book and I'll use it a lot too, a set of wave functions psi j, right? Some wave functions that satisfy this equation, right? Those are orbitals, if you will, are orthonormal, called orthonormal, if they're normalized, right? When you integrate them, for probability, they equal 1, and they're orthogonal. So I'll write that normalized plus orthogonal, orthonormal. If the integral of these two different wave functions that are an equivalent, two different states, integrating over all space, is equal to this weird symbol delta with little m in. Right? I mean, you're going to see this symbol all the time. And this symbol is the easiest function in the entire world. It equals 1 if m equals n, and 0 if m does not equal n. All right? It's a yes or no question. It's literally a yes or no question, right? And the only way, when you do this integral, this overlap integral as we call it, right? How much does these two orbitals talk? They either are the same, and you have probability 1, right? Because they overlap perfectly, they're the same thing, or they don't talk at all. And this is called the Kronecker delta function. And you could just think of it as a yes or no question, right? But this is the real term for it. There's a mathematical formulation for this symbol, and this is made by this guy named Kronecker, and it's called delta function. But you'll hear me call it that, but it's very simple. It's either a yes or a no. Right, and it just tells you whether the indices are correct or not. This is really important. Again, this makes the math so much simpler when we know if we have a particle in a given state, that we're guaranteed that the other states don't mess with it. Right? They're totally separate, as if they don't exist. Questions? Yes?
So what does the long D mean? Didn't mean it to sound like that, but
Yeah, let me write it. So it's a function that either gives you a 1 if the indices are equivalent, or 0 if they're not equivalent. That's all it is. Right, so if you have two wave functions that are labeled m and n, right, these may be your quantum numbers, right? This is the 1s and the 2s, so it'll be 1 and 2. Well, 1 is not equal to 2, so this value is 0. Right? Or if these were both 1s orbitals, then you would get a 1. All right, and what we're going to do is, it turns out that any system you want, any quantum mechanical system, there always exists a set of wave functions you can define for it that are orthogonal. Right? And we're going to do this process over and over and over again. Right? The reason why the hydrogen orbital has the 1s, the 2s, and the 2p is because that's the orthogonal set of orbitals or wave functions that satisfy all the equations for a hydrogen atom. Right? They're constrained with this assumption that they don't mix at all. And for instance, when we look at vibrations of molecules, we're gonna show that all the different vibrations, right? You might have a wave function corresponding to a stretch, one corresponding to a bend. Each of these states have a wave function associated with them, and they're orthogonal. So if you stretch a molecule, it will never bend, right? It will never turn into a bend or vice versa. It's a first order at the very least. So that's the assumption we'll make. So that's a really nice thing to do. That makes our math really easy. Because then all we have are very simple, we can, when we calculate the states of a system, right, when we calculate the orbitals of the hydrogen atom, we can just list them off. And we know for a fact that they don't communicate with each other. They're all individual and separate. And that's the idea. So all orthogonal states are inherently, this is not a technical term, lonely states. They have no concept of anything else, right? They can't talk to anything. And so if we know that an electron's in the 1s orbital, we know for a fact that it will never be in the 2s. It must do something to the atom to excite it. Okay. So we have wave functions that satisfy an equation with operators, right? Satisfy this equation that when you put a wave function as a wave function, that is, if you put it into an operator and you get the wave function back in a number, then it's a valid wave function for that operator. And we can always guarantee that we can come up with a set of wave functions that don't mix or don't talk to each other at all. They exist separately. And that will simplify the math a lot. Okay, almost to the end. Did I hear a question? Yes.
So
Cody.
I noticed for your, you're always choosing, I don't know if this matters or not, you're doing a complex number for the m. Is it you?
That's totally arbitrary.
I was just going to say.
Yeah, it's arbitrary. If you flipped it around, you'd get the same answer. Yeah.
But one of them has to be complex.
Yes.
Okay.
Well, it turns out you can also define, so for instance, the hydrogen orbitals, the way that we'll define them mathematically is that they're always real. So there's going to be tricks where we can combine things together to make them real. But you can, the assumption is that they may be complex. So they're not always complex, but they might be. So if these two wave functions turn out to be real, then all you're doing here is just squaring the function.
You're just leaving it alone.
Yeah, there's no i's to flip to negative, if you will. Yeah, so just keeping it as general as possible. Okay. Now, the next postulate is not 6.
Oh.
It's 2 prime. We're going to come back because
Wait, what?
yeah. So hold on a second. Hold on a second.
Where did it come from?
All number conventions go out the window.
I know this is stupid. So I wanted to introduce this one because it's actually a modification of the idea of an operator. Okay. But I couldn't define this rule because we hadn't learned about orthogonality and all the eigenvalues and stuff yet. So now let's go back. Now that we understand these things or we've talked about them, let's go back and be more specific about operators. And it turns out that operators not only have to be linear, they have to be what's called Hermitian, which is a really weird word. Hermitian operator.
And I feel like we're learning
And-
language.
I know
It
it.
doesn't matter.
Again, this quantum mechanics is honestly the first moment in physics or in science that is global, right? This is something that was done by the world, and there's not really an example of where physics has been created by a global community. It's been created independently by different cultures, but this is a global one, and so it pulls things from math and pulls things from physics and it pulls things from different countries, and so it's just like a jumble of vocabulary, unfortunately. But they're all well defined. They're just kind of strange. And what this means actually is very simple. All physical observables, right? Everything you ever measure in your laboratory, and this is a good one, must be real numbers. All right? So if you apply an operator to a wave function, it has to give you a real number back. Right? You can't measure complex numbers in real life. Right? They're not real. It's just like a what's it called? Well, anyway, I can't think of the word I'm thinking of. Just like complex numbers are just a formula of fabrication, if you will. Right? They represent something that isn't something you actually measure in real life. There's mathematics that has to be described with complex numbers, but when you measure something that is described by complex numbers in real life, you only see the real part of it. This requires operators to be what's called Hermitian. And because we're doing things with calculus, the definition of Hermitian is kind of weird. Later I'll give you a different definition of Hermitian that's much simpler to understand, but we haven't gotten there yet. Which means they satisfy a very simple equation. Well, not a simple one, but not too bad. Which means they satisfy this. All right, so we have the integral of psi squared times our operator, psi across all space. All right, so we're calculating the average value of this observable that's corresponding to operator A. This, in order for it to be Hermitian, It means that the entire thing must be equal to the complex conjugate of itself. Which is, sorry, the complex conjugate of itself. Which would be the integral of psi, the complex conjugate of the operator. So for instance, the momentum operator had that IH bar, the minus IH bar, so the complex conjugate would be plus IH bar times the complex conjugate of the wave function. All right, so what that means is that the average value of A must be equal to the complex conjugate of itself. All right, this is just a real number, right? As we just said, when you take a complex conjugate of a real number, nothing happens because there's no i's in it. So basically what this means is that the i's cancel out in the end. Right, so that the operator is its complex conjugate, which means it's a real number. Okay. So so you can come up with any operator you want, right? I just gave you a list of them, but maybe you could come up with some crazy one, right? You could be, for instance, maybe we could come up with the Haywood operator. What's your favorite function, Bobby?
2f of x.
Well, give me something more specific then. All right, the Haywood operator. Just give me something. Do you like sines, tangents?
Yeah, let's do
Just give me something. Make it up. Anything.
sine x cosine x.
Right. We might very well be able to apply this and come up with a set of wave functions that satisfy. What variable would you like for your observable? Little h?
Yeah, little h. That'd be great.
All right, we could solve this equation. Maybe this isn't the best one. Let's add an I to it. Actually, this might. Yeah, let's add an I to it because I think this actually comes out. So let's add an I to it. Right, I could come up with a set of wave functions that satisfy this, but this is not a Hermitian operator. So that means that this is not a real thing, right? We would never observe H here. It's not a real observable because its corresponding operator is not Hermitian. What this means is that the operator might give you an I, which means that its complex conjugate is not equal to itself. And that means you would never actually observe it. Okay. So that really limits things, right? That's the thing, is that every rule that I've given so far means that we have pure freedom to pick whatever we want to look at, right? Something crazy, right? We could ask at the tangent, or the e to the x sine x cosine x over x to the fourth plus 5. Right? We can come up with any operator we want, and maybe solve for the wave functions that satisfy this equation. But that operator might not be Hermitian, which means we won't physically observe it. Right? If we came up with an instrument to measure the Haywood operator, we would never be able to do so, never be able to measure anything because the operator corresponding to that measurement device is not Hermitian. Right, so that limits the kinds of things that we can ask. Right, and that's why when I made a list of the operators that we can make, it's very short, and that's because most operators that you can come up with aren't Hermitian. And that means that there's not a real physical thing you can measure for. Okay. So now you maybe understand why I call this 2'. So that I've constrained our operators to be very specific. They have to give real numbers out. Have to. Now here's an even cooler one. And this is the second to last. And then we'll be done for the class. Number 6. This is number 6. And then we have 7 and then we're done. And 7 is one that we won't look at until spectroscopy. So I just want to write it down and have you guys know it because we'll need it for spectroscopy. And it's called completeness. Now, I don't think the book calls this a postulate, but I like to call it a postulate because I think it's really important, and it's the key to being able to do anything, calculate anything in chemistry. All right, so assume we have a set of wave functions. psi of I, right? Some sub that satisfy this equation. And we could say it satisfies the Schrodinger equation or something, but just any old operator. Right, we put an operator on of A, we get an eigenvalue A sub I back. And again, we have to say that A is Hermitian. So we're guaranteed that the little a is a real number. We can write a new wave function. Let's call it big psi. Mr. Pitchfork I, psi. Such that, let me write that for you. Big psi is just a linear combination of little psi's times some coefficients. And this equation satisfies the same equation. This satisfies the same equation as before. That A big psi operating on big psi gives you some value times psi back. Okay, so what this means is that you can bootstrap things. So let's imagine, for instance, let's go back to hydrogen now. Okay, so little psi's are our hydrogen orbitals. Okay, we have a 1s orbital, a 2s orbital, and so on. Okay, all right, and our hydrogen orbitals satisfy the Schrodinger equation. I'll just write it here. So our set is the psi 1s, psi 2s, psi 2px, and so on. Okay, and these satisfy the Schrodinger equation, and when we apply the Hamiltonian to them, we get the energies back. Okay, all right, so this is the hydrogen atom, hydrogen orbitals. Now, let's go to. Now, maybe we want to do it for helium. What about helium? Well, helium turns out to be a much harder thing to calculate. As we'll see that you can exactly calculate all the wave function and all the energies of hydrogen atoms. It's exactly solvable. But helium you can't. So that's a problem. Well, if we can't solve the Schrodinger equation exactly for helium, how do we ever calculate anything about helium? Well, the trick is that you can take a helium orbital. So let's say we want to calculate the wave function for helium, the 1s orbital of helium. We can write it as a linear combination of hydrogen orbitals. Like that. So that might mean then when we do the math, we calculate these C values. I should write that. Let me write one more thing. There's one more constraint. The sum of the squares of these values is equal to 1. Right, so they're normalized. Right, we're guaranteed that we can take this formula. We can represent our helium orbital that we can't solve for as a linear sum of hydrogen orbitals that we can solve for. And we can do that for any system. So the idea is that you can bootstrap complexity, right? We start with a very simple problem, which is the hydrogen atom. And the way that we're going to represent more complex atoms is by representing the wave functions, the states of that atom, with a sum of simpler ones. And so when you go do, if you're in computational chemistry, you want to calculate the energies or the properties of anything with quantum mechanics. Maybe you use programs like Gaussian. There's all sorts of different programs to do these kinds of solving the Schrodinger equation for chemical problems. These are programmed with the idea that complex problems like the helium atom or anything bigger than that, you can't solve exactly. So what they do instead is create these systems of simpler functions that we can represent a more complex wave function with. We guaranteed that this works. So this is guaranteed to work. there always exists a set of you're always guaranteed that there's a simpler set of wave functions that you can add together to represent a more complex one. This is molecular orbital theory. Remember, with molecular orbital theory in organic chemistry, we took atomic orbitals and we added them together to make molecular orbitals. That's exactly what this process is. We know that while we have a problem representing the orbitals of molecules, we don't really know what they look like, we can't solve for them. So what we're going to do is we're going to take these molecular orbitals and represent them as linear combinations of atomic orbitals. Right? Maybe you've seen this. Linear combination atomic orbital molecular orbitals. Right? This is exactly the process that you do. Right? So all of chemistry, all of computational chemistry, all of quantum mechanics for chemistry uses this as its power, because you know there are going to be very complicated problems that you can't solve exactly. So instead we're going to solve them as a sum of simpler problems. And this is literally molecular orbital theory.
I'm confused as to like in the like summation up there, what does the H and N equal?
Oh, sorry, this is hydrogen. These are hydrogen orbitals. That's what I meant by H.
Oh, okay.
Yeah. So you have some set. I should do this I. Sorry, because the sum is I. My bad. Right, and these are just. I'm saying that you can represent a more complex wave function state as a sum of simpler states. So in this case, the helium 1s orbital is a sum of hydrogen states. And of course, this might be infinite. It might go on forever. But you can imagine that the helium 2s orbital is very similar to the helium 1s orbital is very similar to the hydrogen 1s orbital. So this coefficient is probably pretty big because there's a lot of 1s character. And there might be a little bit of 2s, but very little 2p, right? So these C3 and C4s might be really, really, really small. They're not zero, but they might be close enough to zero that you can get rid of them. Right, and that's exactly what atomic LCAL MO theory is. Linear combination is that you take a simple combination of atomic orbitals, add and subtract them together to get a more complex orbital for your molecule. Okay, how much time do we have? Okay, well I can't get to the last one, but that's okay. We'll do it tomorrow. Any last questions? All right, so this gives you all the rules to solve anything in quantum mechanics. You literally have every rule you need to do to solve anything for a molecule. If you want to know what a molecule looks like, what its properties are, you have everything here. Now that's harder said than done, unfortunately. So what we're going to do starting on Monday and literally for the rest of the semester is we're going to come up with examples from real life. Hydrogen atoms, spectroscopy, all sorts of different systems, and we're going to apply these postulates in order to be able to model and calculate the properties of molecules and atoms. You guys have a lovely weekend. I'll see some of you in 50 minutes. And I'll see the rest of you Monday.
Are you trying to prepare the coding?
Yeah, let's do it.
Yeah.
Party.
Today's a new day.
It's a new day. It's a new day.